So today, like I said, we'll review the little bit that we've already done back in Unit 4 and some of Unit 3. And then we'll start talking about drawing the structures. Tomorrow's when we will start to get into what's called VESPER, which is valence shell electron pair repulsion theory. Sounds way more complex, guys, than it is. What do we know about electrons already? They're negative, all right? They're negatively charged, and what do negatives want to do? Or like charges want to do? Spread out, guys. They will repel each other. So what VESPER is just the theory that governs the shapes of the molecules. Like I said, we'll get there tomorrow. We'll talk more about it. Here we go. Review. You're checking your work from the homework yesterday. So this was a question, guys, that you had in your that you had to answer yesterday as well. We did talk about this back in Unit 4. So it's talking about bonding in polyatomic ions. What you want to remember, guys, within the ions themselves, all right, you have covalent bonding going on within the ions. When they're bonded to other stuff, you have ionic when it's bonded to other pieces. All right? So if you looked at your list of polyatomic ions, if you had those in front of you, you would notice that all of those ions are made up of nonmetals. All right? Every single substance in those polyatomics are nonmetals. So therefore, it's covalent. They're sharing electrons. All right? We're going to learn how to draw structures for polyatomic ions here in this unit. When you bond them to other things, though, the ions, like, say, sodium carbonate or calcium carbonate, your chalk from your lab. Guys, calcium is a what? It's a metal, right? It's got a 2+ charge. Folks, polyatomic, it's in the name, ions. So when the ions themselves as a whole bond to other pieces, they have to be ionic bonding because they're an ion. Now, I know we say metals and nonmetals are ionic bonding. That's just kind of a quick way for us. Really, guys, the bigger concept is ions bonding to ions. That's what it's dealing with. All right? So within the ions themselves, you have covalent bonding taking place. Everything's being shared. And then when you bond it to other stuff, there's the ionic piece, that electrostatic attraction. All right, Lewis dot diagrams was a review. All right, so what's the easy way to figure it out? First off, what do valence electrons show? I just said it wrong, didn't I? What do Lewis dot diagrams show? They show the valence electrons. Valence electrons are the outermost. What's the easy way to figure out number of valence electrons? Look at the periodic table. What tells you on the periodic table the number of valence electrons? The what? The group number. Right, so ions, guys, when it comes to ions, the basic ones, the neutral atoms, they're easy. You look at the group number, that tells you the number of valence electrons they have. Helium, again, has only got 2 valence electrons, even though it's in group 18, because the first energy level is satisfied with 2 electrons. Now, when it comes to ions, they have a charge. They've either gained or lost electrons. Beryllium, what's the magic number they're all trying to get to? 8. Is beryllium going to lose 2 or gain 6? Lose 2. So when we draw the beryllium ion, we're going to draw the symbol like we've seen. We're going to put brackets around it. It's going to have a 2+ charge. Will it have any dots in there? No, because it lost its electrons, guys. So that's all you would draw for your beryllium ion. It's got to have the brackets because it's got a charge. Now, oxide, on the other hand, oxygen, what's the charge it's going to have? 2- because it gained 2 electrons. It'll have 8 total electrons. How many dots will it have? It'll have all 8 filled in. We did do this, guys, back in Unit 4. It's been a while, though, so I can understand why we don't remember it. So you'll want to go back and check and redo all your ion ones from your homework last night so that you have those in there. Not going to take the time right now to go through them all. You guys can figure it out. This is new here. Hybridization, guys. When you have a hybrid of something, what is it? It's double. It's 2 things combined into one. So whether it's it's a hybrid car where it can run on electricity or gas, or if golfers out there, a hybrid club. It's between a wood and an iron. All right. So you did it. It's mixing up 2 more, guys. In relation to chemistry, It's the mixing of two or more atomic orbitals of similar energy, and it makes new orbitals of equal energies. So this is what's happening here. Now, I'm introducing it. We won't deal with it a lot specifically beyond this, but this is really what's happening within bonds of molecules. So you've got similar energy. So like you've got the s orbital, or the s sublevel, and you've got the p sublevel, which is 3 orbitals with it. All right? So they are close in energy, but they're not the same. So what's the whole idea of bonding? To get to 8, which makes it lower energy, right? They're happy. There's a lot of strain when you just got these extra electrons out there. So we've said before, guys, atoms and molecules, they're lazy just like us. They want to exert the least amount of energy possible. So what they will do, these orbitals will combine together into hybrid orbitals, which will be overall lower in energy than these two separate ones. So you've got the S and the P separated, and they will become what's called an sp hybrid orbital. Notice, guys, where I drew that. I drew it in between the S and the P so that overall the energy is lower total. All right, it's in between because they've hybridized. So here, this would be like saying this one is the S, and then you've got the 3 P's right there. All right, so it'd be like sp3 hybrid orbital is what we get there. Something like that. Okay? We're introducing it. Don't stress yourselves. Just know, guys, with hybridization, it's the mixing of 2 or more so they have equal energies. That's what you need to know. More of a concept than actually applying it in this class. Those of you who take AP may go on and do more with it. So here's our examples, guys, for carbon. What we're going to do first is we're going to draw the orbital notation. What's orbital notation? The boxes with the arrows, guys. So remember, what are our sublevels? I taught you the way to remember it. They're the letters. SPDIF in that order. S, P, D, F. How many orbitals does the S have? 1. P has 3. D? Right, there's that pattern. So for carbon, guys, first things first. Write out your noble gas notation for carbon. What's our noble gas we're going to use for carbon? Helium. All right, so then he's scared of the first 2 electrons. Then it's what? 2s2. 2p2. Okay? So, now we're going to draw our boxes, guys, that correspond to these. So S has got 1 box. P has got 3. Now we're going to draw our arrows in there. 2 questions I have. These will both be prize questions. All right, so raise your hand if you shout it out. No prize. First one is, why do our arrows go in opposite directions? This is a good review question for next Thursday's test.
Spin.
Okay, you got to be. I'm looking for a term. All right, they do have to have opposite spins, but what states that they have to have opposite spins? It's a term I'm looking for. Pauli's exclusion principle, guys. They have to have opposite spins. No 2 electrons can have the same set of 4 quantum numbers. That's review from Unit 3. All right, so there's one prize question. Ellie got that one. The next one is, over here with the p orbitals, why did I spread them out into each individual orbital first before doubling them up? Okay, lowest amount of energy, absolutely. Again, I'm looking for the term. What's the term? So they do want to spread out to keep lower energy? Not off-ball. Good guess, though. Not Heinz. Nope, we haven't had that. What? The raisin guy?
Yeah, he made raisin pudding.
J.J. Thompson? No, that's the electron. That's the plum pudding model. Nope.
Is it like one has to like all?
Right, why? But I'm looking at to why. What's the term that's saying that they have to be that way? So, you always can use your notes for a prize question because all the questions come out of it. I've been said that since day one. Shh. Hund's rule, guys. Hund's rule states you got to spread them out, and it is to keep the lower amount of energy. So, for carbon, all right, I'm going to erase this one, to make it look a little bit better, we've got the p orbitals right here. All right, one electron there. So when they become a hybrid orbital, what will happen is this right here. They become one long one now. The S and the P have combined. So there's 4 on one line. We're going to fill them in the exact same way, just like so. This becomes what we call an sp3 hybrid orbital because we have one S and we've got 2 of those. So we put all of them together, we fill in the boxes, sp3 is what we get. I want you guys to try boron quickly. First thing you want to do, guys, is write out the noble gas notation. So it's going to be helium. It's going to look very similar to carbon. 2s1, sorry, 2s2. Hold on, let me do this and I'll answer your question. 2p1. We do the noble gas, the orbital notation. 1, 2. Our p's here now. Same thing as 3, but only 1 electron is in there. When we go to a hybrid orbital, it's going to be one long one. 1, 2, 3, and 4. So as we fill them in, we go 1, 2, and 3 because we have electrons for that. Folks, up here, how we got this 3 is because this is P1, P2, P3, and here's our S. This is going to be sp2 hybrid that we have there. sp2 because only electrons were in 2 of the P's, not all 3. Does that make sense? Again, you need to know, guys, with hybridization, the concept that it's mixing of 2 separate orbitals to make equal energies. We're not going to have to do this on our test or our final exam. AP Chem, you guys will talk more about it, all right, but we will not worry about it in this class. We've done Lewis structures a little bit in the past, back in Unit 4, so some of this will be review. All right, so then this is where you want to have a highlighter to kind of highlight as we go through it. I'm going to talk through the concepts quickly so that we can get to practicing where it'll make a lot more sense than just talking about it. All right, element symbol, guys, we know that represents the nuclei and the inner shell electrons. Dashes, they represent an shared electron pair. Pair means how many? 2. Keep that in mind, guys. 2. So each dash equals only 2 electrons. Bless you. Dots represent unshared electrons. We call these lone pairs of electrons. All right, lone pairs. And then a single bond, guys, we know that contains 2 electrons that are being shared, like we just said about those dashes. So for every dash you see that has 2 electrons, and again, the key word here is that they are shared. All right, so these Lewis structures, guys, are only for covalent molecules. All right, ionic will have those brackets with the dots and the charges. Bless you. All right, but they will not have these Lewis pairs. So all these rules that we're dealing with are only dealing with covalent. What type of elements, guys, make up covalent compounds? Non-metals. So where are non-metals located? To the right of the metalloid staircase. Guys, the only elements we're going to use are those to the right, and we're not going to use the noble gases. Why won't we use the noble gases? Because they're already noble, which means they have 8, so they won't bond. Okay, so we won't use that. So we're only using a dozen elements or so within these. All right, moving on. Our rules. Okay, I'm going to kind of talk through these, guys. It's easier than it seems by just looking at all these. So we're going to start off with simple structures today. Tomorrow we will get into double and triple bond structures. We're going to add a few more rules and then polyatomic ions as well. Today we're going to keep it simple, go step by step. All right? Follow the process. If you don't follow the process, guys, and you skip steps, that's when your structures will be very difficult to draw because you're not going to have the correct numbers. Here we go. First step, guys, we need to determine the number and type of atoms. From the number and type of atoms, we're going to figure out the total number of valence electrons. That's the piece that is most interesting that we have to know. All right? You've got to know this, guys. Number 2, if you skip number 2, already you're going to be off on the wrong foot and you're probably at the wrong structure. These 2 steps kind of go together, and you'll see why when we do an example. Once we have our total number of electrons, then we're going to make what's called a skeletal structure. This is going to sound confusing, guys. You will see what I mean when we practice. The first atom in our formula is the central atom, unless otherwise specified, or hydrogen is written first. Why can't hydrogen be our center atom, do you think? How many electrons is... What's that? It only gets one what? Not one electron. It only needs one more, so it only has one bond, guys. Hydrogen can only have one dash from it because it's satisfied with two valence electrons. Hydrogen cannot be the center because otherwise it can only be bonded to one thing and your formula, your structure would not be there. So, first atom in the formula, that's going to be your center one unless the problem specifies. And then if it's hydrogen, you go to the second element. We're going to add up the electrons used. All right, so what this means, guys, by used is that we're going to draw dashes. Once we set our skeleton up, our elements arrange those around each other. We're going to draw dashes to connect them. Then we're going to add up the used electrons and subtract from the number of used electrons from the total. All right, we've got to bookkeep as we go along because you've got to use all of the electrons that you account for. If you have 14 valence electrons that each element brings to the table, so for a total of 14, you have to use all 14 of those electrons in your structure. Step 4, we're going to add electron pairs so that each atom has 8 electrons. Remember, hydrogen will only have 2 electrons, which means, guys, hydrogen only has one dash, one bond. All right, it only has one bond. Save the central atom until the last one when you're adding alone pairs. And then step 5, you want to count up the total number of electrons you have in the structure and make sure that the octet rule is satisfied for all atoms. This is as far as we're going to go with our rules today. If they're not satisfied with these rules, then we will go on to another step and we'll talk about that tomorrow. All right? So, now we're going to practice. You're going to see, guys, these rules seem a lot more complex when we talk about them. Once we start to do some practice, it gets much easier. We good? Can I go on to the next slide? All right. So, our first example that we're going to use, guys, is iodomethane. This was actually back at the top part of your rules. So in the little space between the you try or the practice problems, that's where you want to do iodomethane. What's our first 2 steps we got to do? Number and type of atoms to figure out the number of what? Electrons. We're going to figure out the number of valence electrons, guys. So here's what we're going to do for step 1. Carbon's my first one. How many carbons do I have? 1. How many valence electrons does carbon contain? 4. All right. So this is the number of atoms. And this is my number of valence electrons for that atom. All right. We're just going to add them all up. And then we're going to add all the different atoms together to get my total. Hydrogen. How many hydrogens do I have?
3.
How many valence electrons does hydrogen have? 1. Plus, how many iodines do I have? How many valence electrons does iodine contain? All right, so now we're going to add those up. 1 times 4 is 4, plus 3 times 1 is 4 plus 3 is 7, plus 7 is. So we have 14 total electrons that we're using here in this problem. We have to use all 14. Okay? You have to use all 14. So that's steps 1 and 2. We got our total number of electrons. Step 3 says to do what? Arrange a skeleton structure. Well, which one is my center atom? We got to have a centerpiece. The first one, unless it's hydrogen. So carbon's going to be our centerpiece, guys. If you see carbon in a compound, it's going to be the centerpiece. Notice, guys, where carbon is on our periodic table. Where is it? Okay, what group is it in is what I mean. 14. How many valence electrons does it have? 4. Guys, that's the kind of in-between. Does it gain 4? Does it lose 4? So that's what makes it very unique, which it becomes a center structure or centerpiece for your structures most of the time. So we've got carbon in the center. Now we're going to arrange all of our other pieces around that center one. Do you think it matters the order that we put them in? No, I typically start over here to the right and just go clockwise from there. So I've got 3 hydrogens, and I've got an iodine. Could iodine be in any of those 4 spots? Absolutely, guys, it could be. It doesn't matter where it is. All right, just get it in there. Now, we're going to connect these, all right, using what? Bonds, dashes that represent a bond. This is what it means, guys, to have a skeleton structure. You've got your pieces kind of arranged, and they're connected via bonds. Now, in those bonds, in those dashes, what is in there? 2 electrons. So we have 14 total that we could work with. We have now used how many? 8. So guys, these are my bonding electrons. I'm going to subtract those out. So I have 6 electrons that are left over. What am I going to do with these leftover ones? Outside, which are as what? Valence electrons in what? What did it say in your rules? Dots, guys. These are going to be lone pair electrons. So we're going to make lone pairs with these around the atoms that we aren't satisfied. So here we go. We're going to count them up. Hydrogen. How many electrons does hydrogen have around it? 2. Is that enough for hydrogen? Absolutely. So each hydrogen, guys, is satisfied with just the dash. Now, let's take a look at iodine. How many does it have? 2. It needs to get to how many? 8. How many more does it need? 6. So 1, 2, 3, 4, 5, 6. Oh, so I've added those in there. I'm going to subtract 6 out. 0. I've used up all my electrons. All my electrons are gone. When you get those gone, now you're going to go back, guys, as the last step to make sure they are all satisfied with their octet rule. So here we go. We said the hydrogens were already good. Iodine, how many does it have? 2, 4, 6, 8. Iodine's all good. Carbon, how many does it have? 2, 4, 6, 8. They're all satisfied, guys. This is our structure for iodomethane. Questions? Let's go on. Let's practice a couple more. Ammonia. First off, we need what? The formula. What's the formula for ammonia? Not NH4, that's ammonium. NH3 is ammonia. All right. First step is to figure out what? Number of atoms and valence electrons. So, I've got 1 nitrogen. How many valence electrons does nitrogen have? 5. Plus, I've got 3 hydrogens, which has 1, we said. 5 plus 3 is 8. So we have 8 total electrons, guys, to use in this structure. My next step is to make a what? A skeleton. What is going to be my central atom? N. It's the first one, and it's not hydrogen. Put my hydrogens all around it. I'm going to connect them with a what? A line, which is a dash that represents 2 electrons. So how many electrons have I used? These are my 6 bonded electrons. I have 2 that are left over. And what are these leftover ones going to be used as? Dots, which are called lone pairs. We got to get used to using that term, folks. Now, the central atom we save for last, so we're going to take a look. Hydrogen. Is hydrogen happy? Yes. Yeah. So now the central atom is the only one that's left. That's where our lone pairs will go. -2. We have 0. We've used up all of our electrons. Let's count up and see. How many do we have? Hydrogens, we said were good. Nitrogen has 2, 4, 6, 8. There's our structure for ammonia. Easy? You guys try this practice example, silicon tetrafluoride, as well as the 2 you try problems that are up at the top of the next page. This is what your structure should look like. Any questions? All right, moving on. You try. BRI. We have 14 total electrons. All right, each of them brings 7 to the table. Now, with this one, will there be a center atom here? Why not? Because there's only 2, guys. So whenever you have 2 points, you have a what? a line. So it doesn't matter where you put it. All right, iodine, connect those like so. Subtract out 2 bonded electrons. We have 12 that are going to be lone pair electrons. Each of those will have 6. There's what our structure looks like. Now, we haven't gotten into shapes yet, guys, but what shape do you think this is? Of the shapes you have listed on the front of your page, which one do you think it's going to be? It's going to be linear, guys. Now, realize that all those shapes have 3 or more atoms with those. We'll get into this tomorrow. Guys, whenever you have 2, though, it's just a line. Distance between 2 points is a straight line. Therefore, if you only have 2 elements, it's going to be a linear molecule. Here we go, the last one. Carbon has 4, 3 here, 7, so it's going to be 14 again. This is going to be the same structure as our iodomethane, except instead of iodine, we're going to have bromine. H, 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 Br up at the top, and there's going to be 6 dots around it. Questions? Easy? All right, your homework tonight, folks, page 9, and then you're omitting numbers 3, 7, 8, and 10. Those ones will have more of what we're doing on tomorrow. All right?